Okay, good afternoon. I think our presenter was able to present his topic, no, Mr. Lee, no, because a while ago, no, this morning he is also the one who assigned for the software engineering. Okay, so this time our discussion will focus on data memory management. So efficient management of database memory is crucial for optimizing the performance and efficiency of database system. So the memory in a database system serves multiple functions such as storing data, catching frequently requested information, and running queries. Efficient memory management is crucial for guaranteeing optimal performance of the database, prompt response to user queries, and effective utilization of system resources. The buffer pool is a basic topic in database memory management. So the buffer pool is a memory space used by the database system to cache data pages that are fetched from this. So the implementation of this caching method effectively mitigates the necessity of retrieving data from slower storage devices, such as hard disk, hard drive, hence enhancing the overall performance of queries. Configuring the size of the buffer pool is essential for administrator as it depends on the system resources and workload factors. Caching is a crucial of managing database memory effectively because caching is the process of storing frequently requested material and memory in order to decrease the amount of time needed to get it from storage. And this can encompass the caching of query result, indexing of site, and other data structure. Effective caching solutions aid in reducing disk for input-output operations, which are often slower in a comparison to retrieving data from memory. So in memory database, elevate memory management by keeping the complete database or substantial section of it in RAM, no? By adopting this method, the requirement for frequent disk input-output operation is eliminated, resulting in accelerated query, processing enhanced system performance. Nevertheless, effectively managing memory in a memory database necessitates meticulous assessment of the accessible RAM and the database size. Database memory management encompasses query optimization as one of its components, and the query optimization of the database systems select the optimal approach to execute a query by considering criteria such as the presence of indexes, statistical information, and system resources. The optimizer's decisions are influenced by memory management as it must take into account the memory use cost associated with various query execution plans. Concurrency control mechanisms are utilized in a multi-user database context to regulate access to shared resources such as memory. Locks, transaction, and isolation levels are crucial elements of concurrency management, which guarantee that numerous users can interact with the database concurrently without leading to data inconsistency or conflicts. Garbage collection is an essential procedure in memory management that involves recovering memory used by items that are no longer being used. Garbage collection in database systems serves the purpose of preventing memory leaks and ensuring optimal utilization of available resources. Automated garbage collection procedures are frequently employed to detect and recover unutilized memory, hence mitigating the potential for gradual deterioration in performance. As what we discussed during last time, that database system frequently include tools and programs to monitor and optimize memory utilization. Administrators have the ability to examine the memory-related metrics such as buffer full hit ratios, page rates and writes, and overall memory use in order to discover areas of performance limitation and enhance memory configuration setting. Database memory management is troubled by the issue of memory fragmentation, and because fragmentation arises when memory is assigned and released in a manner that results in small spaces between allocated blocks. Over time, this might result in optimal utilization of memory as the system may encounter difficulties in locating consecutive segments of available memory for big allocation, because memory compaction techniques can be used to decrease fragmentation and enhance overall memory efficiency. Last time, we discussed also the virtual memory in database system enables the utilization of a larger memory capacity than what is physical present by facilitating the exchange of data between RAM and disk. So excessive dependence on virtual memory can result in a decline in performance due to heightened disk input-output. Database administrator must meticulously manage the utilization of virtual memory to avoid excessive swapping and ensure maximum performance. Memory leaks, which occurs when a program neglects to free up memory that is no longer required, can have a harmful impact on the database system. Persistent execution of database activities without appropriate memory reallocation can result in a progressive escalation and memory consumption, ultimately resulting in a depletion of available memory in the system. And consistent surveillance and troubleshooting are essential to identifying and addressing memory leaks in database application. I just want to share a video presentation wherein we're able to give you actually that this will be a hands-on application of a memory allocations, no, for database management system.
So welcome back to today's class. And for this particular session, I want us to talk about memory management in Oracle database. Now, as you all know that when we talk about a database instance, this is actually an involvement of two things. We have the memory and we have the background process. We have the memory and the background process. So when it comes to memory and background processes, this equals to a database instance. Now, we all know that when we talk about memory or the Oracle database memory, we are talking about, it's actually subdivided into two sections. We have the SGA plus PGA. So these are two very important memory components as far as the Oracle database is concerned. And of course, the SGA stands for Shared Global Area. PGA stands for Program Global Area. So I know by now that if I give it as an initial, SGA and PGA, you all understand. Now, in these memory components, we also have, of course, we have some sections or components that makes up SGA. We have components that makes up PGA. And if I can just shed some lights on that, you'll find that when you talk about the shared global area, which is equals to SGA, we have these components. For example, we have the shared pool, we have the database buffer cache, we have the large pool, we have the streams pool, we have the Java pool, and the rest. So when it comes to managing, or when it comes to managing memory or memory management, we will end up talking about some of these components, because you see, we will be immersing ourselves so much on either the SGA or the entire memory. That means a combination of both the two. So when we talk about the memory, yes, Robert? I'm good, I'm good. So already the session is on. Yes, so you can continue as the rest join us. Yeah, so for this case, we are talking about managing memory or memory management. That is a topic we were supposed to do it by yesterday. And for this case, we are talking about how can we manage memory. So I've actually started by mentioning the two components that makes up a memory, because when we talk about a memory in Oracle database, we are talking about SGA or PGA. Now, we have something called the database instance. Again, that word, sometimes we end up, encountering that. And of course, this refers to a combination of memory and background processes. So in this case, we are talking about the memory, and we need to understand how can we manage this memory. And of course, management of the memory, of course, again, takes you through to a point where you need to understand the components of each subsection of the memory. For example, the SGA, which stands for the shared global area. And of course, we have some of these components: the shared pool, the database buffer cache, the large pool, streams pool, and Java pool. Now, so talking about management, we have two ways of managing. Talking about management or memory management. Remember, it's about the Oracle database memory management. Of course, we have different ways of managing other types of database, especially the memory. And for this case, I want us to know more about memory management as far as Oracle database is concerned. Now, we have two ways of managing. The memory. And managing the memory means we need to understand its parameter files. Now, one thing we can do here is just to show you the combination. So we have this tool, which is actually show parameter memory. So these are the components that, so if I press enter, you can see that we have a lot of information or a lot of parameters that are involved. This is the memory. But I don't want you to concentrate so much on the upper part. We have the lower part here. And here means that we have to talk about the memory _max_target, which by default is given as 0. We need to talk about the memory _target, which again, the value is 0. So this means that the memory _max_target is of course in disable mode because it is 0. So it means that it is not in a position to maximize or to consume the size of the memory allocated. So memory max target, memory _target. So those are two keywords that we will talk about. Now, again, we need to talk about this parameter, show parameter SGA, or at some point, I can talk about show parameter, okay, let me just have SGA. Now, show parameter SGA, this is one of the component of the memory, which stands for shared global area. And you can see that we have something here called SGA underscore target. So this one is a parameter, SGA underscore target. Now, if you look at its allocation or its the way it's allocated, you can see that the value is not 0, but it is 2192 MB. So it means that out of the space allocated to memory, SGA has already taken care of, has already consumed or has already used 2192, memory, that is the MB. So what happens here is that as far as we want to understand how we can manage the memory, or in Oracle database, we will interact with the SGA underscore target, which of course has come out as a result of us querying this show parameter SGA. And here we have something called SGA underscore target. So if you want to know the size of the memory as far as SGA is concerned, or the size of the SGA allocated, or the space allocated to SGA, then you have to query this show parameter SGA, and you can see this parameter called SGA underscore target, and you can see that it has 2192 MB, 2192 MB. So that is the space allocated. Now, probably the question you're trying, or probably the question is, how can I view the PGA? Now, we also have this parameter, show parameter target, show parameter target, show parameter target. So if you press enter, now you can see it's bringing both sides. Now, what you can see here, you can see that we have these two, memory underscore max underscore target. Now, when we talk about the memory underscore max underscore target, this is the maximum memory allocated. Memory underscore target, this is the memory allocated, the space allocated to the memory. Now, you see, if you allocate 20 MB to memory underscore target, then you can still allocate around 40 or 50 memory underscore max underscore target. So you will always end up having the higher value attached to memory underscore max underscore target compared to memory underscore target. But now you can see that both of them, the memory max target and memory target, the value is 0, 0. Now, here we also have the two parameters here. Both of them are actually allocated. A value has been allocated to these two. Now, this is PGA, PGA underscore aggregate underscore target. This is always a parameter attached or connected to the PGA memory. So you can see that 728 MB of the memory space has been allocated to PGA. SGA underscore target is a parameter connected to SGA, and you can see that it is the value attached to that, or the value assigned, is 2192 MB. So for this case, before even we move, I want you to see this mathematics. Memory underscore target equals to SGA underscore target plus PGA underscore aggregate underscore target. Now, this is the maths I want you to have in mind. So for me to get the memory underscore target, this is actually the target memory size that has been allocated to both of them, to both the SG and the PG. So if I want to get the memory underscore target, which of course by this point, by default is not assigned, then I have to add the SG underscore target, which is being displayed here, SG underscore target, which is 2192, plus PGA underscore aggregate underscore target, which is being given here as 728. So if you add both of them, the 728 plus 2192, you get what we call the memory underscore target. And probably what you're wondering why memory underscore target here is 0 is because of how this memory is being managed. So we are going to have a look at the two types of management, or the two types of memory management. Now, for you to capture all of this at a go, all these parameters at a go, then you can just execute this parameter, which is show parameter target, show parameter target. Now, so that is the formula you want to know. Again, we also have this table, $3 SGA info. We also have this dynamic performance view table, which is actually called SGA info. If you press enter, you can see that we have these columns. Now let's see what is happening. Let me choose all of them. Select name, bits, resizable, con underscore ID from $v SGA info. Okay, I think there's a resizable size. Yeah. Now this is what this is. I've actually selected everything from that table. Even without, I could even use select star from $v SGA info. Now, what this tells me, you see, it's giving me almost the sizes of the SGA components. So just picture out the way we did discuss the SGA memory or the SGA components or the shared global area components. And of course, you can see that we have been based on this, what is being displayed here, you can see some related information. For example, Java pool, large pool, shared pool, streams pool, we have buffer cache. Now, all this makes up the SG. All this makes up the SG. So you can also see, of course, we also have added information here. You see, even if you want to get the free SGA memory available, you can still look at it. But the most important thing is that each one has been allocated a space. A space has been allocated in terms of, I think it's KBs. This is in form of KBs. Now, the resizable here, represented by res, you can see there are those columns or rows that have the resizable no. So if resizable is no, then it means that you cannot adjust. The system allocates automatic the bits. You see, it allocates the bits automatically. Now, those that have the yes, it means that they are adjustable. You can readjust them. So for the no, you cannot adjust them. For the yes, you can adjust. Adjust means you can alter that size. If it is 46.97, you can still even reduce it to 20 something. You see, that is the adjustments I'm talking about. So it's allowed for you to adjust these SGA components. So those are the few things I want to probably talk about as far as memory is concerned. And of course, we have these parameters. There's so many parameters you can use. You can use show parameter target. You can use show parameter memory. So if you talk about memory, show parameter memory, if I repeat it, you can see show parameter memory can give us this. This is only connected to the memory. Of course, that memory is a combination of both SG and PG. So you can see memory max target memory underscore target. Here, we do not have any SG underscore target or memory, or PG underscore aggregate underscore target. Now, if you want to go to the other side, now this is where you can use what? The target. So the target can give you everything on board. The target can give you everything on board. So you can see we have the memory max target, memory underscore target. We have the PGA underscore aggregate underscore target. We also have the SGA underscore target. So having learned about these parameters, it is now high time for us to understand the management or how can we manage memory. So here you can say that Oracle database memory can be managed through the following methods, ways or methods. So you can have, like, number one, we have something called automatic. So we have the automatic memory management. This is represented by AMM. You will always find us talking about AMM. Number two, we also have the same thing, but this time around we have the automatic shared memory management. Shared memory management. This one is ASMM. So here we will talk about AMM and ASMM. So just to know what it stands for, because that is the shortest route or the shortest way we can talk about them, rather than going a long way and having a full meaning. So automatic memory management, that is AMM. Automatic shared memory management, that is ASMM. Now, for automatic memory management, if I can just talk about it a little bit before we look at the practical part of it, you'll find that the automatic memory management enables specification for total memory provided for both the SGA and PGA. Let me repeat. AMM provides the total memory. So here I can say AMM provides, let's say, provides the total memory for both the SGA and PGA. You see, that is AMM. It provided. So if you combine the total memory size for SGA plus PGA, then of course that gives you or takes you to an automatic memory management, which I'm actually talking about it here as AMM. Now the allocation is set in a, you see, there's a point I was telling you people that there's no way that SGA will surpass the PGA in terms of in terms of the memory consumed, in terms of the its operation, because SGA always ends up having more components than PGA. So we can say that the allocation of space, or the allocation, is set in a 60-40 ratio. That means 60 for SGA and 40 for PGA. So there's no way that you can end up getting the PGA having more percentage compared to SGA. So even if I talk about the 60-40 ratio, it's not always, because you can end up even having SGA getting 70% and the PGA getting 30%, or SGA getting 90%, and then of course PGA getting 10%. Now, so just to know that for the AMM, it enables specification for total memory provided for both the SGA and PGA. The SGA components will be allocated memory automatically depending on the workload. So as long as you're talking about the AMM, the space allocated or the memory allocated or the memory is going to be allocated to SGA automatically, because you see, based on the two methods, the AMM and ASMM, remember we have S in ASMM. That stands for the shared. And shared means it's actually the SGA we are talking about, because SGA stands for the shared global area. So in this case, it means that when you talk about configuring your database, or when you talk about configuring the memory, not even the database, but configuring the memory as show parameter memory, you'll find that we have these two: memory underscore max underscore target, memory underscore target. Now, let me give you the difference. You see, when you talk about the memory underscore target, this is more dynamic. It is actually the dynamic parameter. It keeps on changing. Memory underscore target is a dynamic parameter, and it keeps on changing. Now, on the other side, you'll find we have the memory max target. Memory max target is the opposite of memory target. So since memory target or memory underscore target is, since memory underscore target is dynamic in nature, then memory underscore max underscore target is static in nature. And you see, when you talk about dynamic parameter, means that it keeps on changing. For static parameter, it ensures that you cannot set the memory target to a value higher than the memory max target. You see? So this is the reason why we are having max. This is the maximum memory target. So there's no way that you can set the the allocated space for memory target that can go beyond or greater than the memory max target. So by default, the system knows what is your max target. And of course, for memory underscore target, this is dynamic, so you can set it based on the given value on the memory underscore max underscore target. So just be careful. Anytime you're given that mandate to adjust the memory components, ensure that the memory underscore target is always lower than the memory max target. Now, so by default, we have two methods or two ways of adjusting. So I have said one method of memory management is AMM or AMM, which stands for automatic memory management. And of course, this one is a combination of SGA plus PGA. This is a combination, and it is automatic, and it is there by default. Now, we also have another one, which is ASMM, probably for Daniel who has just come in. So AMM stands for automatic memory management. And then ASMM stands for automatic shared memory management. So just for the sake of, so automatic memory management, okay. And then of course, which is connected to SGA and PGA. Then of course, we also have the ASMM, which of course stands for automatic, which is actually the same thing, automatic shared memory management. Okay, memory management. So don't worry about that, but at least you have a clue. So the question is, how can we switch? You see, we need now to learn or to understand this concept. As long as we are talking about management or memory management, we need to understand how can we switch from AMM to ASMM, and how can we reverse it from ASMM to AMM. So there are two questions here. How to switch, or number one, switching from AMM to ASMM. And another one, switching from ASMM to AMM. So you see, it is the opposite of each other. And this is the practical part I want you to know. Now, another point is that, you see, when your memory management or when your memory is in AMM, it means that the system is managing the memory for you automatically. So it means that you do not have any interaction with the memory. That means you cannot alter the memory unless that memory is in the second method or in the second part, which is actually ASMM. And again, something here. For AMM, it is actually a combination of both SGA and PGA. For ASMM, this is only tuned to SGA. It is only tuned to SGA. So that is why we have the letter S, which represents shared. So I want us to start from this perspective. I want us to start from switching from AMM to ASMM. That is where I want us to start from. How can we switch the memory from AMM to ASMM? So I'm going to give you a step-by-step guide. So just understand the topic, how to switch from AMM to ASMM. And then of course we will reverse it. So here it means that of course I'm going to have it, okay. So I'm going to have it. So number one, I'm going to give you like procedure. I mean, the first step probably as you write it, or so that I do the practically part of it. So first of all, we need to determine the total memory currently allocated to SGA. So here I can say, first of all, number one is to determine, determine the total memory allocated to SGA less unused space. So that is what we need to do. Unused, okay. Instead of space, let me just use unused memory. So you see, here we are talking about the memory which is purely allocated to SGA. But as long as you see, you can allocate like 70, but only that is used. So we need to get what is being used by the SGA. What is being used by SGA? And this means that we need to execute a query. You need to execute a query.